Hi everyone, my name is Nanoom Lee. I'm a fourth-year PhD student at New York University, working with Yasin Ali-Hamoud and Roman Skoshimaro. As one of parallel talks of Cosmology from Home 2022, I'm going to present one of my work with Yasin, in which we try to probe small-scale baryon and dark matter Isocurvature perturbations using CMB anisotropies. Here, by small scale, I'm referring to the scale smaller than one megaparsec. This is the outline of my talk. I will first spend 2 minutes to advertise our new recommendation called Dirac-2. And then I will start talking about the main topic. First, by briefly mentioning the motivation of this work. And then I will talk about how we put constraints on small-scale initial power spectrum and the results. We released a new recommendation called Dirac-2 in 2020. Before this new code, the code called Request was most commonly used for CMB data analysis, even though there are much more accurate codes such as Dirac and Cosmology. The advantage of using this less accurate code was the speed. This is brief comparison between these codes. And our new code Dirac-2 encompasses both strengths, the speed and the accuracy. We achieved this by using pre-calculated and pre-tabulated correction function to Lyman alpha escape rate, which is a function of temperature and also cosmological parameters. With higher order integrator implemented, now this new code is even faster than Request, but keeps the same accuracy as the original Dirac. You can find and use this code from my GitHub repo shown here. And if you want to see the details about how we wrote this code, feel free to check our paper. Good. Then I will start talking about the main topic of this talk. As you already have seen from the title, we have tried to probe small-scale baryon and dark matter Isocurvature perturbations. The fact that CMB anisotropy data cannot probe initial conditions on small scales motivated this work. There are constraints on small scales from CMB spectral distortions, but they are weak. Here we use CMB anisotropies to put constraints on small scale initial power using the fact that the small scale baryon perturbations can induce nonlinear contribution to free electron abundance. In the early universe, photon and baryon form a hot plasma. And as the universe expands, the temperature of the universe decreases. And at some point, proton and electrons start to recombine for the first time in the history of the universe. So the photons are decoupled. This is called the cosmological recombination. The recombination is a nonlinear process simply because it happens when proton and electron meet each other. So the recombination rate depends on number density of baryon squared. So if there is any small scale baryon perturbations, it will modify the average free electron abundance. Since CMB spectra is very sensitive to recombination history, this allows us to put some constraints on small scale baryon perturbation amplitude. This idea was first put forward in Yedamzik and Abel 2011 paper, where they use a simple model to calculate the effect of a small-scale baryon clump induced by primordial magnetic field on CMB anisotropy spectra. Here we take a more general way, where our results depend on the total full evolution of small-scale baryon perturbations. Our method I'm going to show soon is general in a sense that it can be applied to any small-scale baryon perturbations, regardless of its origin. But here we consider Isocurvature perturbations as the origin of small-scale baryon perturbations. Then, what are the Isocurvature perturbations or Isocurvature initial conditions? Different inflation model can give different initial conditions. The single-field inflation model gives the adiabatic initial conditions, which satisfy the following equations on the left, resulting from the equal number density fluctuations for all species. an isocurvature initial condition, which we can consider as any deviation from the adiabatic initial condition, can be produced by multi-field inflation. The current constraint from Planck 2018 CMB data are shown below. According to the constraint, the isocurvature perturbations can only take up 2% of total perturbations, and the amplitude of adiabatic perturbations is around 2 times 10 to the minus 9, which we usually denote by the 1 of lambda CDM parameter AS. And this illustration provides simple but clear understanding of what isocurvature perturbations are. In the adiabatic case, all the initial perturbations are the same, including the 1/3 and 1/4 prefactor we saw in the last slide. And if there is any deviation from this, we call it isocurvature perturbations. For example, if baryon perturbations differ from this condition, we call it baryon isocurvature perturbation, which is shown on the left bottom. In addition to these general isocurvature perturbations, there is one interesting combination of baryon and CDM isocurvature perturbations. This is what we call compensated isocurvature perturbations, where the baryon perturbations and CDM perturbations cancel each other so that there is no net contribution to total matter perturbations. In this work, we consider 4 different isocurvature perturbations. CDM isocurvature perturbation we denote as CI, and baryon isocurvature BI, baryon and CDM isocurvature BCI, where baryon and CDM have the same amplitude of initial perturbations, and finally, the compensated isocurvature perturbations, CIP. As a brief summary of what I have talked so far, we are trying to constrain the amplitudes of various isocurvature perturbations on small scale, using the fact that the recombination process depends non-linearly on baryon density. Then let me talk about how we did it. First, how we calculate the impact of small-scale baryon perturbations on free electron abundance. The recombination rate depends non-linearly on the baryon density, so we can write the resulting free electron abundance as shown here, where NE1 and NE2 are linear and quadratic Green's functions, and delta I is the initial baryon perturbations. If we take the average, the linear term is gone, and assuming the three-point function of initial perturbations vanishes, we get the first additional contributions to free electron abundance, which is nonlinear and quadratic in initial baryon perturbations. Here we assumed the net recombination rate depends on local baryon perturbations. So our result is valid up to K 10 to the 3 inverse megaparsec, since on smaller scales, the spatial transport of Lyman alpha and Lyman continuum photons can be important. So we limit our study with scales from K greater than 1, but smaller than 1000 inverse megaparsec. Then by defining 2 vectors, B and T, which contain baryon density perturbations and also velocity divergence, we can write the average free electron abundance as shown here. And in terms of the dimensionless power spectrum delta I square of K, we get the following expressions. So to calculate the average free electron abundance given the initial perturbations, we need to first calculate NE2, which is a quadratic correction to free electron abundance per unit initial perturbation at each K. To calculate NE2, we modified Dirac-2, so it takes the transfer functions of baryon density and velocity divergence as inputs, and define time-varying baryon density and also the local expansion rate in Lyman alpha escape rate. Then we can numerically calculate this quantity NE2 so that we can get the final average of free electron abundance. Note that we didn't assume anything about the origin of a small-scale baryon perturbation while we try to calculate the average free electron abundance. So this method can be applied to any small-scale baryon perturbations given their transfer functions. But here in this work, we explored the Isocurvature perturbations. These plots show the baryon transfer functions with 4 different isocurvature initial conditions obtained using class for k ranging from 3 to 10 to the 4 inverse megaparsec. What's important here is how baryon evolves during the recombination epoch. In the case of CDM isocurvature perturbation, the baryon perturbation starts from the null and follows the CDM perturbations, so it takes longer time to evolve. So we expect the least impact on free electron abundance, and so CMB spectra. And as expected, the baryon evolves the most effectively in the presence of both baryon and CDM isocurvature perturbations. The interesting common feature we can see here is that the high K mode baryon perturbations decay before recombination. This is due to large photon drag. Even on scales smaller than Jeans scale, before recombination, the baryon perturbation decays. Only after kinematic decoupling, baryon perturbation on scale smaller than Jeans scale starts undergoing oscillations, but until the gravitational force from CDM perturbation overcomes baryon pressure. And these are the resulting NE2. So the important thing is that we fully take into account the time-dependent and also scale-dependent evolution of baryon. And these NE2 are implemented in class code to calculate the resulting CMB spectra. And here I'm plotting the resulting fractional contribution to the average free electron abundance due to the small-scale baryon perturbations per unit total power, with several spectral indices for power law initial power spectrum. As can be seen here, the different initial conditions of the small-scale baryon perturbations have the different impact on free electron abundance. With these results, to put some constraints on the amplitude of initial isocurvature perturbations, we do MCMC analysis using Monty Python 3 with Planck 2018 TT, TE, EE ranging data. We do this with 2 parameterization of initial power spectrum. The first one is the usual power law spectrum, but here the pivotal scale is defined to be 30 megaparsec. And we also use Dirac-delta spike initial power spectrum to see how each mode can be constrained. These are the results. First, for the power law initial power spectrum. The left panel shows 95% confidence level upper limit on total power as a function of a spectral index. The black line is the constraint from BBN. Our results are weaker than constraint from BBN, but our results rely on totally different physics, and also it can be applied to any small-scale baryon perturbations induced even after BBN. So our results are still useful. Also, as you can see in the right panel, our results on amplitude at pivotal scale are better than current constraints from CMB spectral distortion. And the expected sensitivity of CMB S4 can be better than the sensitivity from pixel-like survey using CMB spectral distortion, depending on the spectral index. And this plot shows results with the Dirac-delta initial power spectrum at K0. We plotted up to K 10 to the 4 inverse megaparsec, but due to our assumption, our results are valid up to 10 to the 3 inverse megaparsec. The thing is that our method can be used to constrain each K mode, while BBN constraint doesn't say anything about what scales the constraint mainly comes from. And here I'm showing the triangle plot with an additional parameter characterizing the amplitude of small-scale initial baryon perturbations at pivotal scale, delta I square of pk, in addition to standard 6 lambda CDM parameters. We see that current CMB data doesn't prefer non-zero small-scale baryon perturbations of any form of isocurvature initial condition we are considering here. If it does, we would have seen the larger Hubble constant, resolving the Hubble tension at least a little bit. This is because with small-scale baryon perturbation, the recombination will be accelerated, which results in the smaller sound horizon at recombination. But since the location of CMB peaks are well measured already, we need the larger Hubble constant parameter to fit CMB data. But here we see no chance of resolving the Hubble tension using small-scale baryon perturbation of isocurvature perturbations. And the second plot shows that any K-mode with any isocurvature initial conditions we consider here cannot resolve the Hubble tension. If I briefly summarize, we developed a new formalism for the impact of small-scale time-dependent and scale-dependent baryon perturbations on CMB anisotropy spectra, and did put constraints on isocurvature perturbation amplitude. This will be considered as complementary proof for small-scale initial conditions. And our results are better than current constraints from CMB spectral distortion. And we concluded the small-scale baryon perturbations from isocurvature initial conditions are not very effective to resolve the Hubble tension in this way. This is the end of my talk. But I wanted to mention that in addition to what I talked today, I'm broadly interested in many things in cosmology. There are several things I'm currently working on, including polarized Sunyaev-Zeldovich tomography, also resolving the Hubble tension by modifying recombination history, and also galaxy redshift space distortion, and dark matter baryon scattering. I look forward to meeting you all and talking to many people during this Cosmology from Home conference to share thoughts and get inspired. And thank you to the organizer of this online conference. Thank you.